Have you ever stopped to think about what kind of power it takes to move an entire continent? I mean, we're talking about land masses that weighed trillions of tons, just drifting. Well, today, we're going to get right into it. We're unpacking the engine of our world and looking at the big theories behind plate tectonics.
You know, it all really kicks off with a simple observation, something that scientists like Alfred Wegener just couldn't shake. Just look at a map. You see how South America kind of tucks right into the side of Africa? Is that just a coincidence, or is it a clue to a much, much bigger story? This one question, well, it's the key to understanding how our entire planet works. So here's what we've got on tap. We're going to start with that original idea of continents just drifting around. Then we'll take a peek under the hood, see what's going on beneath the surface. After that, we'll get into the three main theories: convection currents, ridge push, and slab pull. And to finish it all off, we'll look at what today's science says is the real deal.
Okay, so first up, continental drift. This was the game-changing idea that the continents aren't locked in place, but are actually very, very slowly moving across the Earth. Now, it took a while for people to get on board, but this idea, it set the stage for everything we now know about plate tectonics.
But look, this wasn't just some wild guess based on a map. Wegener brought the receipts. He gathered some powerful evidence. I mean, besides the obvious jigsaw puzzle fit, you had identical fossils of plants and animals popping up on continents thousands of miles apart, separated by huge oceans. You had whole mountain chains that, if you pushed the continents back together, would line up perfectly. Even things like coal deposits matched up. These weren't just a bunch of coincidences. They were like fingerprints left over from a time when the world was all one piece. So, if the continents are moving, the next logical question is, how, right? To get that answer, we got to understand what they're actually moving on. So let's peel back the layers of the Earth and see what's going on.
First up, we've got the lithosphere. You could say this is the star of our show. It's the solid, rigid outer shell of the Earth. It's about 100 kilometers thick, and it's all cracked and broken into these massive pieces that we call tectonic plates. This is literally the plate in plate tectonics.
And right underneath that, you have the asthenosphere. This layer is the secret sauce. It's not liquid, but it's this super hot, solid rock that's kind of gooey. It can actually flow, like incredibly thick honey, but over millions of years. This slowly flowing layer is what those rigid plates are floating and sliding around on.
Now, it's super important to know that not all plates are the same. The crust, which is the top part of the lithosphere, comes in two main flavors. You've got your oceanic crust, which is thin but really dense. And then you have continental crust, which is much thicker but less dense. Now hang on to that word denser. The fact that oceanic crust is denser is a huge deal. Trust me, it's going to be a key piece of the puzzle when we get to our third theory. All right, let's jump into our first big theory for what moves these plates. For a really long time, this was the #1 explanation. The easiest way to picture it? Just think of the Earth's mantle as a giant, slow-motion lava lamp. So, how does this lava lamp engine work? Well, it all starts with heat, deep down from the Earth's core. That heat warms up the rock at the bottom of the mantle. And what does hot stuff do? It rises, right? It gets less dense and starts to float upwards. Once it gets to the top, it spreads out to the sides, and here's the crucial part. The theory goes that as it spreads, it actually drags the tectonic plates along with it, kind of like a massive planet-sized conveyor belt.
Okay, on to our next theory. This one's called ridge push. It's less about the plates being dragged from underneath and more about them getting a little push from the side, all thanks to good old gravity.
So this whole thing gets started at mid-ocean ridges, where new plate material is being made. This new rock is hot, which makes it less dense, so it sits higher up, creating a literal ridge or mountain range on the ocean floor. Now, because this ridge is elevated, gravity steps in. It basically causes this higher, raised plate to slide downhill, away from the center of the ridge. The result is a constant, gentle push that moves the plates apart.
And now for our third theory, slab pull. And I gotta say, this one is a major player. The best way to picture it? Imagine you've got a tablecloth, and you put a heavy book right on the edge. As that book starts to slide off the table, what happens? It pulls the rest of the tablecloth right along with it.
This is where that dense oceanic crust comes back into play. Remember we said it was the denser one? Well, here's the payoff. When an old, cold, and therefore very dense oceanic plate meets another plate, it starts to sink down into the mantle. And because it's so heavy, gravity pulls it down with an incredible amount of force. This sinking edge, the slab, acts like a massive anchor, creating a powerful pull that drags the entire plate behind it. This isn't a gentle nudge, it's a huge gravity-powered force.
So we've got 3 different ideas: a conveyor belt from below, a push from the side, and a powerful pull from the front. So which one is it? Is it one of them? All of them? Let's see what the current science has to say.
Well, the thinking on this has definitely evolved. With modern technology, we can see that while those convection currents are for sure happening down on the mantle, they probably aren't the main thing dragging the plates around. Instead, most scientists today agree that slab pull is the heavyweight champion. It's seen as the primary driving force. And ridge push, that's considered a really important secondary force that helps things along.
So here's the main takeaway, the thing to really remember. It's not just one simple answer. The movement of our planet's massive plates is driven by a combination of things working together. But the 2 most important forces in this planetary dance are that powerful downward pull from sinking plates, that's slab pull, and the steady outward push from the ridges, that's ridge push.
And that brings us to a pretty wild final thought. This isn't ancient history. The plates are moving right now as you're watching this. They're moving at about the same speed your fingernails grow, somewhere between, say, 2.5 to 15 centimeters a year. Now, that doesn't sound like much, but when you give it a few million years, it completely reshapes the world. So what do you think our planet might look like 200 million years in the future?